What I have here on the screen is a statement of what's called the complex conjugate root theorem. And it looks kind of messy and technical, but this is really just a statement of what everybody learns in their algebra classes when they first start talking about complex numbers and using complex numbers to solve quadratic equations or any polynomial equation. The idea here is if z is a root, is a complex root, for example, if 4 plus 3i is the solution of a polynomial equation, then the conjugate of this, 4 minus 3i, must also be a solution. All right, must also be a root. That's all this fancy math statement is saying. And what I want to do in this slide is I want to prove analytically that this is true. And to do that, I'm actually going to do something else first. I'm going to prove 4 smaller statements about complex numbers and their conjugates. And then I'm going to bring them all together. And once I have those 4 smaller statements, showing this complex conjugate root theorem is actually just a matter of 4 or 5 lines worth of calculations. So I want you to see really kind of 2 things from this. First, as I go through and I prove these 4 smaller theorems, I want you to see the process. Right? There's kind of a standard approach to proving statements about complex numbers, and I'm going to use them in all 4 of those first theorems. And the second thing I want you to see is how in mathematics we use smaller things to build big things. Once I've got these 4 smaller theorems, I can build this much bigger, much more significant theorem in a couple of easy steps, just by invoking those kind of 4 smaller pieces. All right, so here's where we're going to start. All right, if z is a complex number and c is a real number, then this equation here is 2. In other words, you can kind of factor that real number out from underneath the conjugate, the bar symbol. So the standard approach that we use when working with complex numbers is I'm going to say let z equal a plus bi. Right, just a generic random complex number. This is kind of our standard approach. Right? Talking about z in the abstract is kind of difficult, but once I have this a plus bi form, now I can be much more specific about what the conjugates are. So let's just kind of work this equation here. I want to talk about cz bar. All right, well, I'm just going to do a little substitution here. I'm going to replace z with a plus bi, and that's still all under this conjugate. Right? Now, this is equal to ca plus cbi. I just use the distributive property there. Now I can actually take the conjugate. Right? Ca is a real number. Cb is a real number. The conjugate of this is ca minus cbi. All right, now I'm going to use the distributive property in reverse. I'm going to factor that c back out. And this becomes c times a minus bi. And now I'm done, right? Look back up here. Z was a plus bi, which means that the conjugate of z is a minus bi. Remember, all we do is change the sign of the imaginary part. But look at what I have right here, a minus bi. So I'm going to substitute z bar, and that's what I wanted to prove. I have the conjugate of c times z is equal to c times the conjugate of z. And that's what I wanted to show. This is going to be our standard approach. I'm going to use this in all 4 of these first 4 theorems. Right, so let's see how we can use this for the second one. Now, I want to talk about a sum. All right, I want to show that in English, the conjugate of the sum is the sum of the conjugates. We can kind of split it up this way. All right, well, I'm going to follow the same approach. I'm going to let w equal a plus bi, which means that the conjugate of w is a minus bi. And I'm going to let z equal, now I can't use a and b again. I got to choose different letters. So I'm going to say c plus di, which makes the conjugate of z c minus di. All right, now let's use the same approach I used before. I'm going to look at W plus Z conjugate. This is A plus BI plus C plus DI conjugate. I just did a direct substitution for W and Z. Now I'm going to rearrange these terms. I'm going to put the real parts together. That's A plus C. And I'm going to put the imaginary parts together. And I still have the conjugate of this whole thing. All right, now I'm gonna do a little factoring. I'm gonna factor the i's out of this second part, and now I can take the conjugate of this. This is A plus C minus B plus D I. All right, now I'm gonna undo what I did in the previous steps. I'm gonna distribute this minus into the parentheses, and this becomes A plus C minus BI minus DI. I distributed the I in as well, right? I just got rid of the parentheses completely. Now I'm going to rearrange again. I'm going to put the A and the minus BI together, and I'm going to put the C and the minus DI together. And look at that. Now I'm home free. A minus BI is the conjugate of W, and C minus DI is the conjugate of Z. And that's what I wanted to show, right? If I rewrite this W plus Z conjugate here, this is exactly what I was asked to show. All right, so and let's try another one here. Now we're going to do the same thing, all right, except we're going to do it with multiplication, right? So in other words, the product of the conjugate is the conjugate of the products, right? So let's see what's going on. I'm going to start the same way. I'm going to let W equal A plus BI, which means the conjugate of W is A minus BI. And I'm going to let Z equal C plus DI. And then the conjugate of Z is C minus DI. All right, so let's look at what's going on here. I'm going to do the conjugate of W times the conjugate of Z. Right? That's going to be A minus BI times C minus DI. Now I'm going to multiply this out. This is AC minus ADI minus BCI plus BDI squared. Okay, now let's see what we have here. Remember, I squared is -1, so this becomes AC minus BD minus ADI minus BCI. Okay, now let me factor a little bit again. This is AC minus BD minus I times AD plus BC. All right, now here there's two ways we can approach this. Trying to show that this is equal to the conjugate of the product is a little tricky. We would have to do some kind of exotic factoring on this to make that work. All right, so I'm actually going to take a slightly different approach here. I'm going to calculate the conjugate of the product. All right, I'm going to say what I now know that W bar times Z bar is this thing. Let me come down here. W bar times Z bar. All right, now I'm just going to look at the right-hand side. WZ bar, and I want to know what this is equal to. All right, well, this is equal to A plus BI times times C plus DI conjugate. I got to multiply this out. This is AC plus BCI plus ADI plus BDI squared, and I want the conjugate of this whole thing. All right, so now I'm going to group a little bit, right? I have AC, I squared is -1, so this is AC minus BD plus BC plus ADI. All right, and we'll still have the conjugate here. All right, so now I'm going to take that conjugate. The real part, AC minus BD, stays the same. I switch the sign on the imaginary part. This is AD plus BC. I just flip the addition in there, times I. This is WZ bar. All right, but now look back up here. Compare this line to this line. And you notice that they're the same. AC minus BD for the real parts minus AD plus BC times I. I have the I on the opposite side, but multiplication, you can put the I. As a matter of fact, I'll go ahead and do it. We'll move the I over here. And now they're exactly identical. So this is equal to this. And that's what I wanted to show. All right, I've shown that these two, that the product of the conjugates is the conjugate of the product. All right, now I need one more thing. All right, one more statement before we can come back to the complex conjugate root theorem. I need to show that you can kind of factor out an exponent, right? And this actually follows from theorem 3, right? Theorem 3 said that W bar times Z bar is equal to WZ bar. All right, but here, let's be a little tricky here. Suppose I replace Z with W. Then this says that W bar times W bar is equal to the conjugate of W times W. Now, rewrite this with exponents. W bar times W bar is W bar squared, and this is the conjugate of the square. All right, so you see what I've done here? I've shown that our statement is true for a specific case. I've shown that it's true for n equals 2. All right. Now there's kind of two approaches you could take here. One approach, kind of the more high level approach, is to now complete the proof by what's called mathematical induction. I'm concerned that a lot of the people viewing this video may not be familiar with induction, so I'm actually going to do this kind of the long way, which is I'm really just going to write this out. Right? Let's say I want to look at Z bar to the n power. Right? This is Z bar times Z bar times Z bar times, I'm just using the definition of an exponent, right? Whoops, excuse me. Z bar, and I have n of these. All right, well, our theorem says that these two, looking over here, right, this is equal to the conjugate of Z squared. And I still have all these other Z bars. All right, well, now I can combine these two together. And this is Z squared times Z bar. Z squared times Z is just Z cubed. And I'm going to keep doing this. I'm going to keep combining each of these terms 2 at a time until I get down to the very last one, right? Then I'm going to have Z to the n minus 1 bar times Z bar. So at this point, I've combined all of the terms except the last one. And this is equal to Z n minus 1 times Z conjugate. And this is just the conjugate of Z to the n. And that's what I wanted to show, right? That's my original statement. I'll rewrite that initial part here. And you can see that's what we wanted to show. All right, so at this point, we're finally ready to hit this complex conjugate root theorem. Right? So I need to do kind of what we did before. I need to make this more explicit. All right, so I'm going to say, look, I'm going to say let P of Z equal, you see I want Z to be the root. So let's say let P of X equal a random polynomial, a n x to the n plus a to the n minus 1, x to the n minus 1, plus so on down to a sub 1 x to the first plus a to the 0. All right, just some random polynomial. All right, I know that z is a root. All right, so remember what it means for a number to be a root. That means that if I put z in here, this becomes this, right? I'm just replacing all the x's with z's. And because z is a root, that has to equal 0. That's what it means for something to be the root of a polynomial. All right, so far this is just what I know, right? This is what I've been told to start with. What I want to know is, what does P of Z bar equal? I'm hoping that this is going to equal 0, right? Because if it equals 0, then Z bar is also a root of the polynomial. All right, well, let's see what we have here. All right, this is a to the n, Z bar to the n, plus a to the n minus 1, Z bar to the n minus 1, plus so on down to a sub 1, Z bar to the first, plus a sub 0. All right, now here's where I'm going to start applying my theorems over and over again. Theorem 4 says that I can take these bars that are inside the exponent and bring them outside. This is a to the n, z to the n bar, plus a to the n minus 1, z to the n minus 1 bar, plus all the way down to, this is still really just z bar, right? Plus a sub 0. All right, now I'm going to flash back to Theorem 1. Theorem 1 says because the coefficients are all real numbers, right? Real coefficients. That's these a sub n's. A sub n is a real number. A sub n minus 1 is a real number, and so on. I can take this bar and extend it. I can make this a sub n z to the n conjugate plus a n minus 1 z to the n minus 1 conjugate plus and so on down to my last one. All right, now I'm going to apply Theorem 2. That's the one that said the sum of the conjugates is the conjugate of the sum. It says I can take all, I'm just adding up a bunch of conjugates here, right? So this says that I can make this a sub n z to the n plus a to the n minus 1. Excuse me, these should all be z bars. Whoops, no they shouldn't. These shouldn't. Right? N minus 1 z to the n minus 1 plus so on down to a sub 1 z. And I can put this conjugate over the whole thing. Now you notice I've left this little a sub 0 here. All right? Because he's become just a little bit of a pain in the neck. I can actually slip him under here too. The conjugate of a real number is just the real number, right? The conjugate of 3, for example, the conjugate of 3 is just 3. So I can actually replace this a sub 0 with a sub 0 bar, and it's still the same thing, and that lets me slip it under here. All right, now here's the magic step. Look at what's underneath here. A sub n z to the n, a sub n minus 1 z to the n minus 1. Come back up here to our original assumption. right? A sub n z to the n, a sub n minus 1, z to the n minus 1, plus so on, is equal to 0. This is just the polynomial with the original z substituted into it. So I can replace that whole big polynomial there with 0. And the conjugate of 0, right, that's a real number. The conjugate of 0 is just 0. And that is what I wanted to show. If I substitute the conjugate into the polynomial, it also evaluates to 0, which means that the conjugate is also a root of the polynomial.